Thanks for the introduction. You're good. Thanks all of you for being here. And so it's insanely hot, so I will. So today we are going to talk about these high-dimensional quantum states, and in particular, some work I've been doing to generate them, and also some more recent work on how to study them. And so let's study. Let's start with the. Oops. Let's see if it works. Yep. Okay. So let's start with the outline of this talk. And I will first talk about high-dimensional state, super short introduction. And I will focus mainly on integrated photonics because this is what I do most of the time to generate non-classical light. And I will give you some take-home message on this part. The second part will be introducing a strategy to characterize high-dimensional states, which we call threshold quantum state tomography. I will explain you what it is. I will show you also some experimental results. And then I will give you some take-home messages about that. Okay, so let's start with high-dimensional state. So we know that we can get a very high-dimensional state with a quantum system by playing in two different directions. The most powerful one is certainly playing with the number of parties, because you have an exponential gain in the dimension of your Hilbert space, depending on the number of parties. Nevertheless, for some application, it's also very interesting to talk about increasing the Hilbert space by playing on the dimension of the Hilbert space associated with each party. This is maybe not particularly convenient for quantum computation because it's very difficult to gain a lot of advantage just playing on D, okay? But for example, in quantum communication, this is very interesting because it's easier in terms of loss budget to transmit more information if you encode on a larger Hilbert space for each photon. Okay, so it's not just a matter of how you increase the Hilbert space, but how much, but also how, depending on the application. And we will focus mainly on this D. Okay, so if you want to do that, light is an excellent candidate because it contains many degrees of freedom, which are associated with a very large Hilbert space potentially. So you can play, for example, with the degree of freedom of time, if you want, if we can call it a degree of freedom, and you can encode the information in time bins. This has been studied extensively, very, very efficient way. So here the information is encoded in a series of bins, and depending whether the photon is in bin 1, 2, 3, 4, or 5, you have a different, you have in this case a qubit of dimension 5. Or you can also play with more exotic degrees of freedom, like optical angular momentum. This is very challenging, but it has been attempted. There have been a lot of very interesting implementation with that. Now, this kind of 2 degrees of freedom are particularly interesting in bulk experiments, but they are very challenging in integrated optics, which is the focus of most of my research, because for what concerns the time, it's not easy to create long delay line in an integrated chip. And for what concerns optical angular momentum, well, polarization and angular momentum in an integrated device are very difficult to control. And so when you move to integrated optics, typically the most used degree of freedom is path. So you encode information where in the position of the photon with respect to a specific dielectric waveguide. And nowadays, this is very interesting because you can really create hundreds of waveguides on a single chip. So you can really increase the Hilbert space very much. And here I designed just a sketch. This can be done in femtosecond laser writing or lithography, even in 3D system, integrated systems. But a degree of freedom I would like to explore today with you is frequency. And in particular, encoding information in the color, if you want, of the photon. So you divide your spectrum in a certain amount of bins that are characterized by this Laurentian peak here. And then very similar to what you do with time bins, you encode information depending whether the photon is in one of these bins. Now, if you think about it, this is very interesting degree of freedom. It's very resilient, very difficult to change the energy of a photon, and also is fully compatible with integrated optics. The problem, though, is that degree of freedom is probably too resilient, because one of the challenges here is that if I want to be able to manipulate my information, I have to end up with strategies to have single photon frequency conversion effectively, reliably, 100% efficiency. This is very, very difficult, okay? It's very difficult unless you have that the frequency band space is not particularly large. And when I say not particularly large, I say between 10 and 100 gigahertz. And why is that? Because if I work within this range, instead of using optical frequency conversion, I can use electro-optical modulators. With electro-optical modulators, I can, in fact, obtain a very efficient conversion from one frequency band to another. In particular, it has been shown that if I take two electro-optical modulators and a wave shaper, I can construct unitaries such that I can map, for example, one beam in an arbitrary superposition of n bands. And so I can manipulate my quantum information effectively. These things are still a bit lossy, but it's not really a loss that is intrinsic in the mechanism, and losses are decreasing, okay? And in fact, there have been some experimental demonstration of that, and I will show you some of our results later in this talk. Now, how do I generate, though, these frequency bands? Okay, so not all the people maybe are familiar with that. One possibility is to use spontaneous fold mixing. Now, in the history of quantum optics, if we think about parametric fluorescence, most of the people talk about spontaneous parametric down conversion. Why? Because it's way easier to do spontaneous parametric down conversion in a bulk system. The problem, though, is that if you think about building photonic integrated devices that are CMOS compatible, you cannot rely on that simply because in centrosymmetric material or amorphous material, in the dipolar approximation, the chi2 is 0. So the second order nonlinear response is not 0 in general, but it's very weak. But you can rely on the third order nonlinear response, and you have this forward mixing that is spontaneous. And the idea, let's see if it works. No, it doesn't. Anyway, the idea is that you can picture in your mind like an elastic scattering of two photons belonging to a pump that end up with two daughters photon, and momentum and energy must be preserved as usual. And so there can be also quantum correlation or not between the photon you created. Now, this is theory, but in practice, what happens? Because numbers are very important. I mean, I'm a theorist. You can see it from the type probably, but the good theories should plug in the numbers. Otherwise, it's just chatting because you cannot be able to interact with an experimentalist. So let's make the math, okay? So let's assume I take a piece of silicon of 1 centimeter, and let's assume that I focus 1 milliwatt, which is the typical power of a laser pointer, at 1550, because I'm in silicon, I don't want the light to be absorbed. And I focus on a reasonably tight focus in 10 times 10 micrometers square, okay? And let's assume that I calculate, let's assume that that energy is preserved, phase matching is achieved, all the things that you need to satisfy. And let's see how many pairs I'm going to generate. I start with a flux of pairs, 10 to the 16 photon per second. So a huge amount of photons. And I get 50 pairs per second. Okay? This is a calculation actually that we did with John basically 10 years ago. Now, of course, this is a big problem because it's not a big investment, and this is never gonna work very effectively in bulk unless I crank up the power. Nevertheless, I want to stress that this problem is not related to the fact that spontaneous forward mixing is a quantum process, because sometimes we have the false perception that quantum is elusive, the quantum effects are weak, right? But this is not the reason for that. The reason for which this process is so inefficient is because it's a nonlinear process. And this fellow here, which is responsible of the spontaneous forward mixing, has an order of magnitude in silicon that is 10 to the minus 18 meter over volt square. So it's a tiny number. Nevertheless, if I find a way to enhance the light matter interaction, I can hope to increase the rate. And how do I do that? So there are several approaches. I will talk to you about the one I use, and the way I explain it also in my courses usually is the elevator approach, is the elevator effect, if you want. So imagine that I have two people in an elevator, and let's say that one is light and the other one is matter, and I want to say anything about the probability they're going to interact. Now, I don't know these people. I don't know their mood. I don't know if they like each other or not, right? The point is that there is something I can certainly say, that the probability they're going to interact is inversely proportional to the size of the elevator and directly proportional to the time they will stay in the elevator. So even if they never met each other before, no matter what, if they stay in a standard European elevator, not this elevator that you have here, and for 24 hours, they are going to interact for sure. Okay? So the nice thing is that this works exactly the same with light and matter, and it works marvelously. So we need to find an elevator for light and matter, okay? And the elevator I'm going to talk to you about today is a ring resonator. So in a ring resonator, light enters and from a channel, and part of the light is evanescently coupled to the ring. And the light that is evanescently coupled to the ring, when it exits after a loop, can interfere constructively or destructively with the light that's still entering in the channel. If it interferes destructively into the channel, what is going to happen is that the light will be forced to stay for a while inside the ring. Of course, it's an interference effect. It depends on the frequency. So this particular intensity built up inside the ring will happen only at specific frequency. And in particular, you can link the width of these resonances to the time, the dwelling time of the light in the resonator. And so we have the time in the elevator, if you want. And then the radius of the ring will be the size of my elevator. So if I take a sufficiently small ring and I have a sufficiently narrow resonance, I can boost up the situation. And in fact, the maximum field and intensity enhancement is indeed proportional to this ratio, tau well divided by R. We did this experiment. Actually, in Pavia, my colleagues did this experiment. They took exactly the same amount of power I told you in a silicon ring resonator. You see that the radius is very tiny. It's a very tiny elevator, 5 microns radius. The quality factor of this object is 8,000, which correspond more or less to a dwelling time of about 20 picosecond. Okay, and which seems a small time, but for light, I can tell you that it's not that small. And then you produce 10 to the 6 pairs per second with the same amount of pairs. And if you consider that here, it's not a centimeter, but only 30 microns length of silicon, you have 8 orders of magnitude enhancement of the process, okay? And why this work very well? Because again, it's a nonlinear effect. So if I have an intensity field enhancement in a nonlinear effect, this will power up. So if I increase the intensity by a factor 10, in the third order phenomena, the results will be a 10 to the 3 enhancement. Okay, so it's very powerful to enhance nonlinear optics using the elevator effect. There is also another benefits of that I have the frequency being for free, because not only I enhance the light matter interaction, but that I enhance the light matter interaction only involving specific frequencies. So it's particularly useful because if I pump in one of these resonances, the photons will be nonlinearly scattered spontaneously in combs. And in order to preserve energy, the combs will be symmetrically spaced, such that at the end of the day, I generate this kind of entangled state. Yes?
I take it those numbers were for reasonable experimental parameters in terms of how well these rings could be made?
Actually, these are the real numbers that have been measured.
And what kind of finesse do you have for that cavity?
Who? The finesse. Okay, so let me. Yeah, I said the Q is 8,000, so 1550.
That's enough.
Yeah, 8,000 of Q. Here, the point is that the free spectral range of these rings are more than a terahertz. Okay, so they're huge. So it's not like in a Fabry-Perot that is bound.
The efficiency is then scaling at Q squared, or
the efficiency scaling like the Q cube divided by the radius square. Then we can come back to that okay. Now, and this has been done. I will come back to that point though. And this will be done, and indeed the people generate this kind of state in micro ring resonator. This is the work by the group of Roberto Morandotti, who kind of pointed out that frequency being very useful in integrated optics, although frequency being have been around much before 2017, but in bulk system. And this is another group, another work from another group who worked extensively, the one of Andy Weiner, and then also Joseph Lukens also work a lot in frequency bands. And of course, when I tell you everything, it seems that it's a walk in the park, right? Everything works. So I have enhanced the process. I construct the frequency bin state. I also have for free entanglement because energy conservation. And so we are walking nicely in a fantastic green high park here in Toronto. But in fact, we forgot the third person here, which is the electro-optical modulator. Okay? Why the electro-optical modulator? Because I have now a dilemma if I want to be able to generate useful frequency bin, because on the one hand, I want a very tiny ring, because of course, if the ring is tiny, I have very large brightness. But the problem is that the free spectral range, so the distance between the bin, is inversely proportional to the radii. So as I shrink my ring, I will have less bins, depending on the bandwidth. So I cannot go too much smaller with the ring. Otherwise, the distance will grow more than hundreds of gigahertz. Okay? At the same time, of course, I could take a big ring. I would have more bins, but I will have a small brightness. Okay? And in particular, the penalty is severe because, as I mentioned before, the efficiency will scale 1 over r squared. So, you know, it's a big power. Now, we solve this problem. We solve this problem using a Lego.
Also scale with R, so won't it?
No, the Q doesn't scale with R because the Q is just dependent on intrinsic loss. And intrinsic loss for a sufficiently large Q is independent, or for a sufficiently large R is independent because it's the banding loss, let's say, okay? But if you go in a micro resonator with silicon, if you go above a certain radii, the Q is independent of the radii. Depends on the scattering loss of your system. So you can decouple the two. You can decouple the two. The Q, let's say that at the end of the day, you're right that what matters is the finesse. Let's clarify this. Let's clarify this. So you have essentially a field enhancement that goes Q to the 4 divided by R to the 4. This is the field enhancement because you have 4 fields, and each of them is enhanced Q divided by R. Then the problem, though, is that the ring, the more ring you have, the more matter you have. This is a coherent effect, like a super radiance effect, if you want. So this scale like R squared. So the more matter you have, the better it is. So in a certain way, having a long ring from this part work, but of course there is a penalty here. And then you can see spontaneous forward mixing like stimulated by vacuum power fluctuation. And the vacuum power fluctuation is inversely proportional to the Q, because the smaller is the resonance, the smaller will be the vacuum power fluctuation that stimulate the process. And so at the end, you get Q to the cube divided by R squared. This is the scaling. So we use the Lego approach, and the idea is the following. So this is a work that we came up with John a few years ago. The idea is, okay, I take a small ring with a certain number, with a certain free spectral range, and then I take a second ring. And I take a second ring with a slightly larger radii, and then I use a thermal shifter to align one of the resonance of the two rings. What happens? Since they have a different free spectral range, I will end up with a combo frequency that is like this. And what happens? Here you see there are two bands that have a distance that I can basically control in the only limiting factor is the quality factor of the resonances by changing the right ratio between the two radii, okay? The nice thing though is that both two rings are small ring, and so the process is efficient, okay? And so I can construct a way to pump this ring independently. This seems complicated, but it's not. It's just a Mach-Zehnder that split a pump, the green light, and then it split it in two, one through an add-drop filter entering A, and the other one enter in B. And what I have is that if I pump in the proper way, for example, CW, I construct a state that is the quantum superposition of the state that would be generated by ring A, and the state that would be generated by the ring B if they were pumping independently. And now I saw something similar. When we came up with this idea, I remember actually this idea, to tell you the truth, was inspired by an experiment that I had the possibility to collaborate with Ephraim Steinberg a few years before. when Ephraim Steinberg used a sandwich source to generate the photon pairs in our experiment. And how a sandwich source works? In a sandwich source, what do you have? You generate a state like this, an entangled state in polarization. And the idea is that you pump with a cross-polarized pump pulse 2 crystals that are orthogonally rotated, okay, such that the first crystal generates from a photon VHH and the second generates from a photon HVV, okay? So what happens? If I am able to create, if I'm able to create the pumping conditions such that these 2 events are indistinguishable with respect to the other degrees of freedom, not the polarization, because the polarization, they're clearly distinguishable, okay? What I'm gonna end up is a coherent superposition of the 2 processes. So what I showed you before with the 2 rings is just the frequency version of a sandwich source, okay? With the difference, though, that for the degree of polarization, we have only 2 degrees of freedom, while for the frequency bin, we have many. So we will see that we can scale up. Now, does it work? Because this is theory, so far it's theory. I'm lucky because I can collaborate with very bright experimentalists. Of course, one is here, like Ephraim, but also in Pavia, we have people. And so we actually design and we ask our collaborator at CLAT in France to build the silicon photonics integrated circuit, which is exactly this design. Just to give you the ready here are 30 microns. The loaded quality factor is 150K. Total insertion loss of the chip is 6 dB, and the free spectral range is 710 gigahertz. So for each ring, so doing frequency bin with one of these rings would be possible with an electro-optical modulator. Okay, and then what happened when you align the resonances of ring A and ring B for the pump? Then you have 2 bins here. This is the transmission spectrum, and you can see that the separation is 20 gigahertz, which is much smaller than the free spectral range of the rings. Okay. And so if you pump here, you're going to generate a superposition of A and B for the signal and, of course, for the idler. First, we characterize independently the ring to see that there was a good brightness. And you can see that we could generate up to 10 to the 5 hertz of generation rate for powers that are around 1 milliwatt. So these systems are particularly efficient thanks to this small mode volume and also to the transverse field confinement provided by the waveguide. And that is the CAR that, of course, goes down as the generation efficiency goes up. But then we wanted to see whether we could generate a particular kind of state, because the nice thing of this source is not that it's just a source of frequency bin, but is a programmable source of frequency bin, because in fact, by changing the heaters of this system, I can tweak the phases with which the quantum interference occur. And so we programmed the system to generate a Bell state, phi minus, and then we tested it by a Bell-like experiment. And this is the result. There are no subtraction count, okay? So this is just the raw data, okay? And we violate CSH inequality by 140 standard deviation, which we believe is pretty good, especially because it has been done in an integrated device, okay? And this is super, super clean, okay? There are some advantages here because a big advantage of integrated optics is that basically everything is single mode, because these are single mode waveguides, okay, for a given polarization. But of course, it's a programmable source. And so we want to go beyond just this experiment. We want to characterize the state and maybe produce other state. And so we perform a quantum state tomography. And we, for example, by pumping the state like this, we could generate this 0-0. Then, and this is the way we perform the quantum state tomography. We pump the system, and then we use the electro-optical modulator here and here, pretty much like you would use your polarizer and half or quarter wave plate with the polarization, and then you do coincidence experiment. So you have a complete, tomographically complete set, and then you perform quantum state tomography. And this is the 0-0, which is very easy because we just pump one of the ring, but then we did the 1-1, the other ring, then we did phi plus, and then we did phi minus, okay? And so you can generate a whole bunch of states. I just want to focus that on the fidelity we can achieve, 98%, which is very large, and the purity, which is 99.9. And again, This is mainly due to the fact that there are very few degrees of freedom here that can balance, and therefore the purity is almost guaranteed because there is very little correlation between the degrees of freedom. So there is also an alternative approach to produce frequency band that is instead of using rings with different radii, you can use rings with the same radii. Okay, and now what do? Well, you shift them relative to each other and you create this kind of comb. And now what do? Instead of pumping at a single frequency, you use your pump in an electro-optical modulator. You create a superposition of this frequency, and then you are able to populate these bins. Okay, so long story short, you can create states like this. We did it experimentally up to Q-quart. Okay, and this is another chip we design, and this is the work, the reference work. And I'm gonna fast this results. These what I'm gonna show you here are all experiment. There's no theory here. It's all experiment, all data. So with the same structure, we can generate, of course, qubits. We can generate Q-trits. You can generate Q-quarts, and we can also change the phases of the superposition with a certain freedom. It's not universal, but with a certain freedom. Okay. So this just to tell you that it's an approach, it's scalable. We are planning to do even more of these frequency bands. Here, the limitation is mainly the quality factor of the system, but losses are decreasing as money is pumped into these fabrication facilities. And so we think that this will be scalable. And let's say that 20, 30 bins are already possible with a reasonably complicated chip, but feasible. Okay, so I want to give you take-home message of this first part. Okay, so what did we learn? Okay, first of all, that is not the only powerful ring in the world. We have also micro ring resonators, and they can be enhanced. They can be boosted very well, and they are compatible with CMOS technology. Another important point is that I show you that we can generate frequency bands in an integrated platforms with very high purity, very high fidelity in a programmable way, which is, of course, very, very important. And finally, we saw that this is very interesting by exploiting this sandwich source approach or Lego approach, which is really one of the nice features of integrated optics, because I can really put together an insane amount of different elements that coherently work with each other. Also because I didn't mention that, but if you consider the coherence length of the light I'm generating, this is way larger than the entire chip. So there's no problem of coherence in an integrated chip. So these photons are centimeter long, while the chip is a few millimeters inside. Okay, so it's coherence is the last of your problem. Once the photon exits from the chip, that's another issue. Okay, but inside the chip, the coherence is guaranteed. Okay, so this is the first part. So where we can find some of these states. Now I want to present you some data which are not published or preliminary. It's the first time I talk about this, so this is new stuff, and it's called threshold quantum state tomography. So as I mentioned before already, I'm a theorist that like very much to experimentalists. And so at a certain moment, I thought, okay, suppose that we increase the dimension of the Hilbert space, and suppose that I want to characterize my state. Well, what is the best approach you can imagine? Well, it's quantum state tomography, because you get the entire state, right? And quantum state tomography, you know how it works. So I have to find the density matrix describing my state. And so this is work that comes from Toronto with Dan James. And of course, this is seminal work in quantum state tomography. So the idea is very, very powerful, simple and powerful. So I create a tomographically complete set of measurements, and then I take these results, and then I combine the information obtained by this tomographically complete set of measurements using, for example, maximum likelihood estimation, and then I'm able to reconstruct the density matrix. Okay, and this approach is very, very powerful because, first of all, it doesn't make any assumption at all about the state. And this is very important because in general, I don't have any information. The other important approach can be applied to qubits, in particular in that paper, they also explain how to extend this and so on. Now, the only downside, but I wouldn't say that this is a downside of the method, is a downside of the problem, okay? Is that the problem is that if I take 2 qubits, I need 16 measurements. But if I take 10 qubits, I need 1,000,000 measurements. Simply because this is the amount of free parameters in my density matrix. So that's the information I have to get. But as you can see, this scales badly. It scales exponentially with the number of parties, or in any case, very badly, quadratically with the dimension of the Hilbert space. So I was thinking about something that is quantum state tomography inspired, but try to see if I could make it a little bit more accessible for experiment with large Hilbert space. And so I went back to the density matrix and I said, okay, the density matrix has some important property to be a physical density matrix. So as I mentioned, positive defined and unit trace. And when I do that, I realized that the off-diagonal term in modulus of the density matrix are basically limited by the square root of the product of the corresponding diagonal element, okay? Where the equality sign works when the state is pure, okay? So the question is, can I use this property in the reconstruction of the quantum state? Can I somehow exploit this property? Okay, so and here is the idea of threshold quantum state tomography. So the idea is that, okay, first, let's measure first on the computational basis. And I will get the diagonal element, okay? Now, instead of doing all the other measurements, okay, I'm gonna define a threshold. And I'm gonna say, okay, I define a threshold, and I am gonna check what are the off-diagonal elements whose modulus is above that threshold, okay? And then I will construct a set of projectors that are kind of target to those elements, okay? We develop an algorithm to do that in a systematic way, and it can be done, okay? So what happens? Then I do only those measurements. So I don't do all the measurements as before, but I do a measurements on a set that is certainly not tomographically complete, but it's target only to those elements whose modulus is particularly large. Let's try to understand the threshold here, okay? The threshold, if you think about threshold 0, this is quantum state tomography. So in principle, this method, if you set the threshold to 0, you do all the measurements, okay? With the difference probably that the tomographically complete set, it's not maybe the usual one, but it's essentially the same number of measurements. But then, of course, as the threshold goes up, you have less measurements. But of course, you are losing information, okay? So if you think about the threshold, this is basically like a limbo bar, okay? So, and of course, if you think about quantum state tomography is extreme limbo, okay? So you really need an athlete when not always, obviously, but if the dimension of the Hilbert space is very large. It's challenging. It's very difficult, right? We would like something more like a theorist could do, right? Something like this, okay? He has a tie, so I'm not saying anything more. Okay, so anyway, so we want something a little bit more like this. So depending on the mood and the skills of the athlete that you are, we want a way to say, okay, you don't have the best equipment in the world, but you still want to reconstruct the density matrix. Okay, tell me the resources you have. I tell you the threshold, and you're going to do those measurements. Of course, it's impossible you're going to reconstruct the matrix with the same precision. Well, we'll see about that. But still, you will have a density matrix. Because otherwise, in any case, you won't get anything, right? So something is better than nothing. Okay? And so, once I have those measurements, I elaborate the information I get, for example, using maximum likelihood estimation. This is what we did so far, but this is not the only way. I won't show you some results, but we also use machine learning to reconstruct the density matrix. When I started, when one of my students started with machine learning, I thought it was a fantastic idea. Then I realized that as the Hilbert space increases, you need so much energy to train your machine learning model that because obviously all people tell you that machine learning is nice and cool and fast, of course, when it's trained, but you have to train that. That's an insane amount of energy you have to take into account, okay? So at the moment, I have to say the maximum likelihood estimation is the best approach that we found so far. Not necessarily the best, but certainly the best we found so far. And so let's see the result, okay? No, let's see first what are the properties. Now, notice I'm not making any assumption on the state. I didn't say the state is particular state, okay? I'm just using, can be applied to any state. The number of measurements can be adjusted on demand, okay? The downside, but if you want, it's not completely downside, is that, of course, the accuracy of the final results depends not only on the threshold, but depends also on the state representation, not the state representation, which is the density matrix I'm going to reconstruct, okay? Because you take the same state, you change the basis, and the representation can be sparse or not, obviously. Now, let's see how does it work. Let's see how does it work. So first, I'm a theorist, so I didn't bother experimentally. So I said, okay, let's do some simulation. Okay, let's take a state like a W state. Okay, and this is the density matrix that we reconstruct with this approach. This is a W state dimension 4. Looks, I mean, for the people that are familiar with W state, they will recognize that that is in fact a W state. We use a threshold equal 0.1 because there is no noise here. So it's enough that you say something a little bit less than 1/4, and then basically all these elements won't be measured. But of course, in the maximum likelihood are estimated, so they're not 0. Okay, and then the measurement that we performed were 28, and you would have and the fidelity is 99.5% with respect to the state that we target. It's not 100%; it cannot be. We didn't expect that, but it's very close. If you do quantitative QST, you would have needed 256 measurements because this is what the measurements you need. Okay.
Sure. But you started with something that was perfect.
Yeah, absolutely. Yep. And of course, we did the same with the W state. Sorry, this is the reconstruction. Okay. And in this case, the threshold we set it insanely low, but it wouldn't have mattered. Even 0.05 would have been okay. The number of measurements 170. The fidelity is 98.9. And of course, for the QST, you would have required much more measurements. But of course, as Ephraim pointed out, this is theory first. There is no noise at all. Okay. Of course, we have taken a state where the representation is a matrix that is essentially sparse. Because obviously, if the matrix is completely uniform, well, you need all the measurements. Okay. But this is in any case, you can do anything about that. So here the point is that this is a method whose convergence will be discovered later, okay, if you want, okay, but or at least when you measure the diagonal elements, and then you will see if there is any advantage, and if you cannot perform, you will have an higher threshold.
I just mean I think the fidelity that you get is a little bit misleading. You're giving yourself too easy a task. So if you have it slightly contaminated.
Yes, this is contaminated because this is an experiment. Okay. It's not 100% because I am asking my maximum likelihood to estimate a number of elements that is way more than the elements of the data that they gave. So and so that's it's I can understand.
Errors on even all the non-zero elements. Finite data.
Yeah.
Okay, so similarly the finite data set, you let your maximum likelihood estimate non-zero value everywhere.
Yeah. Yes. I didn't assume that because it would be not fair. No, I didn't measure them, so I cannot assign them. It wouldn't be fair. Okay. So even in theory, it's not perfect. Okay. Now, initially, I contacted a couple of experimentalists to do with photons this experiment. The problem is that getting large Hilbert space at the moment with photons is challenging, especially discrete Hilbert space. Okay. And so at a certain moment, someone, I don't remember who actually told me, there is the IBM quantum computer You can do that. Okay. Oh, great. So the experimentally was useless at the time. So I did it myself on the IBM Q. Now, and so we produced several circuits on the IBM Q using Qiskit to generate states up to 7 qubits, just because that was the free part. If you want more, you have to pay. Okay. So I am Italian after all. Okay. So just kidding. But anyway, and then I tested threshold quantum state tomography, right? And so we generate, for example, a circuit. We did it randomly. So I'm going to present a selection, but I can tell you it's a representative selection. Okay, but then we will discuss. So first, the nice things of IBM is that it allows you also Qiskit to do quantum state tomography with an over complete set. They don't have the complete set. They use not 4 to the n measurements. They do 6 to the n measurements. I don't know why. Maybe it's easy from a circuital point of view to perform all the 6 to the n measurements. This is we ask a state that most likely, well, this would have been 0 in the target, okay? But the reconstruction of the quantum state was done by IBM like this. This is a 4 qubit, and you see it's 1,296, not 156, because it's 6 to the n, okay? But this is the measurements that they use. So I quoted that. It's not the minimum amount you need. And then I use threshold quantum state tomography. I set the threshold 0.2. And you see, it does a reasonable job. So there is noise here. There is everything. It's a real system, okay? And the first things I ask myself is that, okay, what I should compare the result with, okay? And my first point, I think it's fair to compare with this. Because this is the most precise measurements in principle I can get, right? And so I compare with this, and we calculate the fidelity. The fidelity is 97%, okay? But then I was curious, and I said, so I asked my colleague in Trento who performed this, the calculation with Qiskit. I said, okay, could you please calculate also the fidelity of the 2 density metrics, okay, with the target state that we ask the computer to do? Look at that. The fidelity with the target state for the QST is 0.939, and the fidelity, yes, and the fidelity with the target state of the QST is 934. So it's basically the same, okay? Because in both cases there are errors, okay? The funny thing is that it seems as if I gather with the 28 measurements all the information that could be possible to gather to arrive as close as possible. Yes.
It's a beautiful result, by the way. One thing that would worry me, and I'm actually pleasantly surprised that these two numbers come out so fast, is whether your technique wouldn't have built-in bias and always overestimate the fidelity with these simple sparse states, because by construction it's looking for something sparse.
No, I don't. I let Maxim likely to do what he wants. We also did it with non-sparse. It doesn't change anything.
Well, it won't change anything because you're not measuring all the things that would give you those non-zero values. So I wonder if you would systematically underestimate some of the non-zero terms once they're below the threshold.
You know, as a matter of fact, when we got this result, I was surprised too, because from these, that is understandable. Because I throw away only small numbers anyway. Okay, so it's true that I did a measurement, but they're small. Okay, so most of the information is there in a sense. Okay, the point is that, as I said, these are not far from the target state, the same, and also not only the fidelity. The fidelity sometimes is not particularly meaningful because it's an integrated quantity and so on. But even if you calculate the distance of the matrices, so the normalized distance between each element's module square of the matrix, the distance between the 2 and the target is the same. It's basically the same. Same order of magnitude. There's no difference. Yeah.
But how do you choose the threshold?
Yeah. We took the threshold because we said, okay, let's look at the number at the column that are particularly when we do the measurements of the diagonal. We just keep, in this case, it was easy to choose the threshold because there were only 4 elements that were particularly high. And so we choose a threshold below that such that we're done, okay? But of course, you could also decrease a little bit the threshold and add more information, more measurements. But as you can see, I don't think that the fidelity would increase because it's already larger.
There's something that confuses me more, which is, sure, you've measured all the data, so you
Yeah.
have information about how much contamination there is on the data. But without measuring the off-add between, let's say, a small element and one of the
Mhm.
you have no information about whether it's coherent or incoherent.
Correct.
And that might not show up in fidelity, but it's
Absolutely.
really important for error correction.
Yeah, but yes, but the coherence will be on a small on an element that's statistically small. That's the point. Suppose that the state is mixed. Suppose that the state is mixed. Okay. Suppose the worst that can happen, the state is mixed. There's no coherence and so on. But that state, the probability you get that particular state, it's exactly the element on the diagonal. And if it is sufficiently small,
But there's a big difference between a 1% incoherent error.
Yep.
And a rotation that gives you 1% error that gives you a 0.1 error.
well, it depends on the representation, of course. But you see, I mean, we're just
to see what it does with two different trial states. One that has a coherent error, one that has an incoherent error, because it seems.
okay.
I
So
understand how the maximum likelihood chooses between them, because I think the likelihood should be the same for states that.
yeah, it will. Yes, of course. You will have these elements here that will fluctuate.
Yeah.
Of course. But that error, just can I go on a second, because this way it's easier to finish because there is more. Sorry, just a second. There is more. So we also try with something that was less sparse. Okay, this is less sparse. And again, we did the IBM QST, and again the fidelity with the target state, it's essentially the same. Okay, and the fidelity with each other is basically here though. Since we have some elements here, like this one, for example, we had to make more measurement, not 22 but 72. Still, it's interesting. The fidelity is good. But then we move on to 7 qubits. Okay, and again, 91% fidelities between the two. But look, exactly the same fidelity. Exactly. In order to have a different fidelity, I have to go to the 5th digit. Okay, so it seems to me that although I did only 1,000 measurement instead of 280,000. Okay, now to be fair, this is 6 to the n. The quantum state model would have required less than that. Yeah, no, it was not okay. Still, it seems to me that all the important information was there, in the sense that the distance between my matrix and my state was more or less there. Okay, so I finished. Then I'm super happy to answer every question. So take home message part 2. Okay, so first of all, you cannot. Sorry, there is a mistake. Sorry. No, you cannot fool nature. No, you can't. Sorry, you can't. So you cannot fool nature. Not the journal with the same name. That's from Giacomo Cooking. It's not mine. You cannot fool nature. Okay. So if you want, oh, that's so bad. So anyway, if you want to reconstruct really the matrix, in my opinion, it's clear that you should get your 2 to the n. If you want to be sure that any state will be reconstructed, and you ask me, what is the minimum number to reconstruct any state? That is quantum state tomography, 2 to the n. You cannot do better than that, okay? But you can be lucky. Sometimes you can be lucky, in the sense that if you measure the diagonal elements first, you realize that, oh, I get some information, and that information is, you didn't choose a dummy basis, and so you can, in fact, only most of the information will be contained in certain measurements and not in others, okay? And of course, another important point is that sometimes, even if you are not lucky, times matter. So I think that the nice things of this approach is not only that it gives you a nice results, because I show you objectively a very good agreement between the two methods. But the point is that even when we have to choose a threshold that is very large, and maybe the fidelity won't be 90%, but it will be 80%, okay? this method can be the difference between having a density matrix that kind of resemble and verify what you were looking for, or not having any, okay? Especially when the Hilbert space gets large. Now, I show you just the result 7 qubits, simply because we actually tested with simulated data with noise, with the same noise of IBNQ up to 14 qubits. 14 qubits. The problem is that you cannot plot the matrix because you don't have enough pixels in the projector, so you cannot even plot it, okay? And we reach fidelities larger than 90, even with noise, with 14 qubits. Of course, we need 16,000 measurements for 15 qubits, so, but less than the 100 million measurements you would have needed with a tomographically complete set. And so I think that from this respect, let's say, is a step forward in the implementation of the reconstruction of states, because it gives the possibility to someone to get an idea. Sometimes he will be lucky, and that idea is precisely the right answer, but sometimes no, but he will get something. And with this, I want to acknowledge a number of people, the people from University of Pavia, of course, John from Toronto, people from CLT, and also Fondazione Bruno Kessler, who did most of the picture. Danielle in particular did fantastic pictures with these futuristic colors in the density matrix, okay? And I thank you for your attention, and I'm happy to answer questions.
Okay, so any questions from Martha?
I have a few questions, if that's okay. So first of all, for your threshold quantum state tomography, you mentioned you're not working with a tomograph for a complete set of observable.
Yep.
So how do we know that the threshold that we set has a unique single state that it corresponds to? Is it possible that a single threshold corresponds to these off diagonals that we're measuring?
Absolutely, absolutely. And in fact, the problem is that you will have. So obviously, when you well, obviously, there's nothing obvious really, but so when you perform the maximum likelihood estimation, you will end up with a matrix, of course. But the point is that since you are feeding your algorithm with a limited number of data compared to the number of points that you are determining, because the matrix is more value, there is an infinite number of states that will be compatible with the measurement that you did. The point, though, I didn't show it here. You can calculate a lower fidelity, a fidelity bound, below which you cannot go, even if you didn't do those measurements. Okay, we have prepared communication. We have the expression of that. You can make an estimate. Okay, and so there is a phi bound that even if you want to measure those elements, your state will have a fidelity that is certainly not smaller than this bound. If your state is the target state, because you don't know it, obviously, now you hope that. And this is very important. This is something I didn't say, but this is very important, because in the case of quantum state tomography, the advantage is that you know that you should get the state. It's a very, very good method to get a state, right? But if I start telling you that I don't get some of the measurements, you may question, if you imagine that you find a fidelity that is the fidelity bound, imagine that is 60%, and you find 40%. Well, in that case, you know for sure that the state that you're looking for is certainly not the one you're target, not the one you're comparing the fidelity. Of course, you may find 80%. Okay, it may be or not. Okay, but the farther you can obtain is 60. Okay. Now, in some cases, the fidelity bound is basically related to the sum of the elements that are below threshold on the diagonal, is related to that. In some cases, the fidelity bound is very, very large. In other cases, very, very low. It depends. Okay. But you're right. So in general, there is not a unique answer. And in fact, if you think about it, well, these are two matrices which are compatible with the target state, okay? And you know, so they are different from the target state, but with the same distance. So one of the questions that I asked myself when I found consistently these numbers that are equal, I mean, not exactly equal, but very close, I asked myself, so what does it mean? It means that probably even quantum state tomography because there is noise, cannot in any case reach completely the state, because obviously the noise will prevent you to get some information, right? Okay. So it's not, but of course there are many possible solutions for the same amount. Yeah.
But also in principle look for confidence intervals and calculation.
Yeah. Yeah. And you know, and another, so I think that there are two things that are related to this approach that have to be absolutely explored much more extensively. I did. Okay. One is first, is maximum likelihood estimation the best way to treat the information I get from this limited amount of measurements? I don't know. Second, the effect of the noise. We couldn't study the effect of the noise on the system here. Why? Because the problem is that I don't know really where the noise is coming from. So the noise must be studied, for example, numerically. When I introduce, for example, a Gaussian noise, a Poissonian noise, then I have information about the noise, and maybe I can understand how the method reacts to that. But this one is not a good way to understand that.
Sorry, my follow-up question is actually related to the noise because the slide
Yep.
brought up the
Mm-hmm.
comment on how the noise mechanism in these IDF processes that would impact the whether or not we see
No, I don't know. I don't know. Let's say that about the noise, the problem here is that I don't know which kind of noise I'm dealing with. But one thing that I can tell you is the following. Suppose that we want to characterize a parametric source. In a parametric source like the one, for example, that Ephraim has in his system, where you generate light by spontaneous parametric down conversion, the main source of noise typically comes from multiple pair generation, okay, which are misleadingly counted like a coincidence of the photon of the same pair, but they're not. That comes, okay, and that is as a Poissonian noise, okay. Now, interestingly, I believe that this method would be particularly robust with respect to Poissonian noise. Why? Because the noise will be larger on those elements that I'm going to measure, because they will be up the threshold, and the noise will be smaller on the measure that I'm not going to do. So the effect of the noise will, in any case, be negligible on what I'm measuring. If you take the Gaussian noise, though, that's different, because if I have the same amount of noise on everywhere, I don't know. But you see, that's another important point. So I'm convinced that not all the kind of noise will impact the results the same. But of course, you can always lower the threshold. No? So obviously, I show you super easy limbo. Okay, if you want more, go standing. but in some cases, you will have today, instead of 26 measurements, you will make 100, 200, 600. Fine, until you can.
Any other questions?
I just wanted to say that depending on your system, the number of measurements might be the relevant resource, or it might also be the time you spend acquiring data. I do think that there's another valuable step you could take in addition to what you've already done, which is to vary the amount of time spent on each measurement.
Oh, yeah.
Probably in proportional to how large that element is.
Yeah, yeah, yeah.
And depending on the kind of state, there might be an additional large advantage.
Yeah. No, that's a good
Probably
question.
not an issue.
No. That's a good question. That's a good question. And in fact, you know, let's say that this is a first attempt to go in the direction of not thinking like a theorist, but thinking like an experimentalist. Because in the past, of course, you could be a theorist in the sense that nobody could produce a 14-qubit state. And so I can imagine that I have an ideal state, and nobody's going to try that anyway, right? But now that people start to produce very large states, you realize that some proposals are simply impractical. They are theoretically perfect, but they are impractical. So my approach is, okay, let's try to understand how to make it possible to extract the most of the information. And so you're right. So here, for example, you can further improve the situation by saying, okay, if I have a large elements, I will spend more time on these and all the related elements because of that modulus, because they are more important than others. And so I can tolerate also, I cannot tolerate an error like the one that I have. That's absolutely a good point.
Maybe I just ask.
Yeah.
So if I understand correctly, this works best if you have a good sense of the right representation to use. because you're extracting these matrix elements in a certain representation. And if everything was sparse, diagonal, you perfect.
No, I wouldn't say that, in the sense that I don't need to have a sense of the representation, in the sense that I don't need to have an hypothesis on the state, okay? But it's true that this will work well if the state representation is that one. But I don't need to assume anything. I don't need to have a sense.
So what do you have to bring to this for it to work very well?
Yes, I need to see when I measure the elements when I measure my system in the computational basis, okay, I will see immediately whether it makes sense to try this method, because I will count the number of elements that are significantly small, and I will be able to say, okay, I want to measure a certain number of quantities. So let's say that from the first measurement, I will have a sense that the method will be useful to implement or not. Because if I find that all the columns are identical, don't even bother, because you have to measure everything, right? In that case, you should change the base.
Well, that's okay. So that's the next question. Is there a strategy for, before you implement this, using the set of experiments that you would use to identify the
I think that is a kind of a chicken and egg problem, because at a certain moment, in order to find the best basis, you'll basically need to know the state.
Yeah.
So you can continue to change the basis until you find that there are very few elements, until you find one element, because you find a basis that contains the state. But I think that at the end of the day, if you try randomly, you will probably end up with there is not randomly. There is adaptive quantum state tomography. There is adaptive quantum state tomography. There are approaches like that. The only problem is that, as far as I know, but I'm happy if someone can point me to other paper, this kind of adaptive quantum state tomography have been tested on very small systems, like 1 qubit, 2 qubits, 1 qubit, 2 qubits. Okay, so so honestly, it's very difficult to know if, but that's another approach, of course. Try to follow the state. Yeah.
You're going to take down in small systems for practical reasons.
Yeah.
We did some work on that as well. I believe that on the theory side, for nearly pure states, there's a quadratic advantage to doing it adaptively.
But yes.
The experimental problem is it would be nice to choose whatever basis you like, but then you have to make entangling measurements. So it might not be in your toolbox. But if it is, I think in principle it works even.
Oh yeah. We also try this method with non-local measurements, for example. But again, I didn't want to push farther in that direction, because experimentally I found it less meaningful. And so as you see, I obviously here it's very difficult, because this kind of work, there is the impression that you are kind of cheating. There's always this impression, because you do better than the people before. So, but the point is that here I wanted to be practical. The point here was, okay, let's think about something that can be done, not just that is 100% right. Okay.
And in that sense, it sounds a lot like Fresco's classical shadows technique. So I'd be interested to see how
shadow tomography, you mean?
Yeah,
but in shadow tomography, you don't reconstruct the density matrix. You reconstruct the expectation value without reconstructing the density matrix. So we went through compress sensing, shadow tomography, adaptive quantum state tomography. There are, in some cases, of course, there are hypotheses on the state, like dense quantum state tomography, the sparseness. Here, I'm not saying that it is not a requirement. It may, obviously, if it is not sparse, in order to get a better fidelity, you will have to lower the threshold.
Okay. Any other questions? No, let's maybe thank Marco again.
Thank you very much.